Hello everyone, and this is day 9 of the hands-on workshop, Parallel Programming and Optimization with Intel Architecture. Let us begin. Today we will talk about optimization of memory traffic, and there is one more day left tomorrow where we will talk about using the Intel Math Kernel Library and Intel vTune Amplifier XE. You will continue to have remote access for 5 more days, and during these days I will send you email suggestions for additional labs and additional exercises to do, or you are welcome to take your own code and try experimenting with it. I also have a new announcement today. So Intel has recently started what they call the Intel Modern Code Challenge, and this is a contest open to students and I believe researchers. Maybe it's just full-time students. But the idea here is that they will provide uh, an application code which has background in natural sciences, and people are going to contestants are going to optimize this code for performance. They will submit the code sometime in late October, and then the fastest code wins of those which will be correct. And there are really great prizes, including scholarships and internship at CERN and trips. Colfax is actually running the cluster for this challenge, and this is the page where you can go and visit and see if you're eligible and if you want to take part in it. I want to remind everyone that this course has a web page and recordings of previous sessions are posted online. This is the URL, colfaxresearch.com/how-15-09, and you can see recordings of the previous sessions up through session 8. And also the slides that I'm using and the code that we're playing with, they're all online. If you have a hard time navigating to this page, just go to colfaxresearch.com and go to training web-based, and you will find your way from there. Our book is there for you. It has more than 500 pages worth of discussions of parallel programming and optimization techniques. All of the topics discussed in this training are also explored in the book. The exercises that we're doing are actually labs from this publication. Remote access is active. If you do not yet have remote access and want to get it, please shoot me a message in the question panel. And remote access will be active for a week following the last presentation tomorrow. If you attend 6 sessions out of 10, we will be happy to issue you a certificate of accomplishment in the fundamental level for this course. Visit us at colfaxresearch.com. We have tutorials, case studies, downloadable code, video courses, presentations, a lot of material on parallel programming with focus on Intel architecture. So, because today we are discussing a new topic of optimization, it makes sense to revise what led up to this discussion. We are talking about Intel architecture, focusing on Intel Xeon processors and Intel Xeon Phi coprocessors. And throughout this course, my goal is to share my own experience and convince you as well that it is possible to have one code base for both platforms, meaning if your code is highly parallel and it has good memory access pattern, then it will run well on Xeon Phi as well as on Xeon. And there is just one set of optimization techniques and one general approach to parallelism that applies to both platforms. This slide relates to performance, and specifically it addresses what we are going to talk about today. I showed this slide during the very first presentation on day 1, and it shows a measurement of the memory performance in terms of bandwidth for two platforms, as usual, a dual-socket Intel Xeon CPU shown in green and a Xeon Phi coprocessor shown in blue. So what's happening here? I have an application that allocates it allocates three large arrays in memory, A, B, and C, and then it uses all cores to read array A, multiply it by a number, add to array B, and write back into array C. This is called the triad test in the industry standard benchmark for measuring memory bandwidth called STREAM. The STREAM benchmark is well known, and there is a white paper on the Intel site discussing how to compile the STREAM benchmark for optimal performance on Xeon Phi. But basically what I'm doing is I'm reading a large array from memory sequentially, and I'm doing something with it, and I'm writing it back. The results are measured in gigabytes per second. This is how fast data travels from memory to cores and from cores to memory. In the case of Xeon, this is straightforward. The CPU is talking to its system memory. And in case of Xeon Phi, the cores of Xeon Phi are talking to the onboard memory in Xeon Phi. So there is no PCI Express traffic here. I'm just talking to the memory on the card. And Xeon Phi gives me about twice as high a bandwidth as a Xeon. Then the next step is where I modified the STREAM benchmark and I added a little bit of randomness in the memory access pattern. So instead of reading and writing huge arrays, which are many megabytes in size, I'm reading only 4 kilobyte, a 4 kilobyte block with each thread, and then this thread has to jump to another memory location and do triad on another 4 kilobytes, and then jump again, and so on. So there is randomness in the memory access pattern, and the penalty for this randomness on Xeon is almost a factor of 2, on Xeon Phi almost a factor of 3. And if I add even more randomness, and I read only 1 kilobyte and then jump in memory to another location, then there is further penalty on Xeon, but even greater penalty on Xeon Phi. As you can see, that neither platform really likes memory access pattern that has randomness in it, but Xeon Phi is much less forgiving of such a pattern. This is just a reminder to programmers that the memory access pattern, in addition to parallelism, is a prerequisite for good performance on Xeon Phi. And today we will talk about how to actually minimize memory access with the help of specialized programming techniques. By the way, anytime I show such a comparison plot, I'm comparing one Xeon Phi against a dual socket high-end Xeon processor of the Ivy Bridge architecture. I'm never comparing against one core. I'm not comparing against one socket because I want to compare devices of similar thermal design power. So today we will talk about memory access optimization, which holds the 4th position in the list of optimization areas which we propose as the optimization roadmap. It doesn't mean that it is the 4th most important. This is just the methodology. The order of they are ordered in the order of best approach to methodology. But in fact, as far as performance goes, memory access may be the most important aspect of the optimization after multi-threading. The key to optimizing memory access is usually data locality. And once again, I want to remind you that we are talking about optimization from the perspective of already having an algorithm and expressing this algorithm so that it can use the hardware in the optimal way. We are not talking about picking the best algorithm. Instead, we are discussing implementing given workloads in code so that the compiler and the platform are best able to run it. So data locality is what you want to achieve in your algorithm. Data locality helps to handle cached memory systems both on Xeon and Xeon Phi, but it is especially important on Xeon Phi because Xeon Phi has less cache per core than a Xeon, and the way that the caches operate is more energy efficient. At the same time, it is less forgiving. For example, there is such functionality as prefetching, and this functionality in Xeon, for example, is carried out by specialized hardware units called prefetchers. They train to the memory access pattern, and then they recognize, well, the application is reading this memory address, and judging by what it did in the past, it will want the next memory address so many cycles later, so why don't I fetch it ahead of time so that by the time the core needs this data, it will already be in the cache. There are prefetchers in Xeon for fetching from the main memory to level 2 and from level 2 to level 1. In Xeon Phi, there are hardware prefetchers for fetching from the main memory to level 2, but not from level 2 to level 1 caches. It doesn't mean that there is no prefetching. You can still use the compiler will still try to implement prefetching in software as best it can. But at the same time, you can see that you really need to express your code in such a way that the compiler can understand what's happening. Also, data page walks. This is a situation that occurs when you have too many jumps in memory, like this stream benchmark modified with randomness that I showed earlier. Data page walk occurs when you are trying to read a virtual memory address for which you do not have an entry in a special cache called TLB. TLB stands for Translation Look-Aside Buffer. It exists in every core, and it maps some virtual memory addresses to physical memory. If you don't if you're accessing a virtual memory address which is not cached in the TLB, you will do a data page walk, which involves communication with the operating system. This is a very expensive operation, just to find where to get your memory, just to find where in physical memory your data resides. To handle all these limitations, the rule of thumb is locality of memory access in space and in time. So locality in space means that your data structures need to be compact, and we already saw an optimization of spatial locality when we talked about vectorization in session 6. There, remember, we had Coulomb's law calculation, and initially we used an array of structures, but then we converted it to a structure of arrays, and this improved performance by more than a factor of 2 on both platforms. If you don't remember this discussion, or if you missed it, you can go back to the course page and view session 6. And actually this screenshot illustrates exactly what I was talking about. This is optimization of spatial locality of memory access. Another aspect of locality is temporal locality, meaning that if you are going to reuse any data, you want to reuse it as soon as possible while it is still cached. And this is what we will discuss today. We will talk about algorithms for improving the temporal locality of memory access. In relation to that, I want to bring up two terms that are useful to know and useful to think about when you deal with memory access: arithmetic intensity and roofline model. Arithmetic intensity is the ratio of how many operations you do on every number read from memory. I'm sorry, I said it wrong. Arithmetic intensity is just how many operations you do on every number read from memory. In other words, this is the ratio of floating point operations to memory accesses. If you have a low arithmetic intensity, meaning that, for example, you read a number from memory, you do an operation on it, and then you go on to other numbers in memory. then your application will likely be bandwidth bound. But if you read a number from memory and do a lot of arithmetic operations on it while it is still in cache, then you're likely to be compute bound. How many exactly operations you have to do to transition from bandwidth bound to compute bound, we can estimate from the from the theoretical peak performance of vector units and from the theoretical memory bandwidth. Let's think about Xeon Phi coprocessors in double precision. They have a theoretical peak performance of 1 teraflop per second. How many data are there in 1 trillion floating point numbers in double precision? Well, 1 times 8 bytes per number, is 8 trillion bytes. So your vector units in Xeon Phi are so hungry that they want to consume 8 terabytes of data every second. Caches can supply this much data, but can the main memory supply this much data? Well, not by a long shot. The bandwidth of access to the onboard memory on Xeon Phi, the theoretical peak bandwidth, is 384 gigabytes per second, and only 50% of that is efficient. This is what this eta factor is for. So if we divide 8 terabytes per second by 0.3 terabytes per second, this is even the optimistic scenario, we get a ratio of 20. So your memory delivers data to cores 20 times slower than your cores can consume it. It means that if you fetched a number from memory and you're going to use it again, you better reuse it while it's still in caches, so that caches can deliver this huge bandwidth. So back to our arithmetic intensity. If you do many more than 20 flops per memory access, then you're likely to be compute bound. If you do many fewer than 20 flops per memory access, you're likely to be memory bandwidth bound, or depending on the nature of the memory access pattern, you may be latency bound, which is actually a poor case. This paper, you can click it, it's a 2009 paper, suggested an analytical tool based on the arithmetic intensity called roofline model. A roofline model is a curve in the space of performance versus arithmetic intensity. This curve has a flat area for high arithmetic intensity, and it reflects the maximum performance that you can get from your application if your arithmetic intensity is this high. And then this curve has a bend at this critical arithmetic intensity that we estimated in the previous page. So in this case, this is 20 flops per memory access. And below that bend, you have a linear slope. So for arithmetic intensity of 1, your performance in gigaflops per second is actually limited by how many gigabytes per second you can move from memory to cores. How is this useful? Well, if you have an application, and for this application, you can estimate how many memory accesses you do. I'm sorry, how many floating point operations you do for every memory access. You can draw a column in this space. For example, if your arithmetic intensity is 4, then you draw a column here. And if you hit the sloping part of the roof line, then you know that you can increase the arithmetic intensity, and it will give you an increase in performance. But if you estimate your arithmetic intensity to be very high, then you know that changing the arithmetic intensity will not do anything, and maybe you need to focus on something else in your application if you're not hitting the peak performance. By the way, addressing a question that just came in, I want to clarify that when I talk about a memory access, I generally talk about reading a single number from memory, even though a single memory access will bring in a whole cache line, which is 8 double precision numbers. So I'm factoring in this this pattern of memory access, that when I read one number, I actually get 8 numbers. So this is already factored in, and I'm assuming that in all these considerations, the memory access pattern is sequential. So I'm not jumping in memory from point to point, because this will invalidate relying on bandwidth completely. So when I talk about memory access, this is reading one double. So if I find myself here, how do I increase the arithmetic intensity? And this is what we will talk about. I will discuss two techniques for, actually I will discuss three techniques for increasing the arithmetic intensity. And one of them, actually a set of techniques, is called loop tiling. The example with which we will study memory access optimization is going to be matrix vector multiplication. This is probably not the most dramatic example in which I can really illustrate how it is important, but it is easy enough to understand. So let's pretend we are doing matrix vector multiplication. Our matrix is A, we are multiplying it by vector B, and the result is C. So A is rectangular, it has shape n by m, so it has m rows and n columns. And I can write a function that takes matrix A and vector B as inputs, and it returns vector C as output. This algorithm naturally has has loop nesting. So it is straightforward to use two levels of parallel hierarchy in Intel architecture. We can parallelize across cores in the outer loop, and we can parallelize across vector lanes in the inner loop. This should work just fine. Let's assume that m is large, maybe it is in the thousands. So I have plenty of parallelism to occupy all of my threads. And let's assume that n is also not too small, maybe it's a multiple of 16, well, at least many more than 16. We can also assume that, well, yeah, let's just assume that n is a multiple of 16. In this case, I can use pragma vector aligned because I expect every row of matrix A to begin on an aligned boundary. This is what we discussed once again in session 6, alignment and the hint pragma vector aligned. And you can see that I have unit stride memory access in the inner loop. I access matrix A with unit stride in J, and I access vector B with unit stride in J. This is not such a bad implementation, but there is one issue. Suppose n is so large that vector B does not fit in the level 1 cache available to each core. In Xeon Phi, the level 1 cache is 32 kilobytes. 32 kilobytes is 4,000 double precision numbers. And in fact, if I'm working with if I'm working with 4 threads per core, well, then maybe I have a little less than that available to each core. So if you think about this algorithm, count how many times will you have to use every value of B. For example, B0, how many times do we use it in this entire algorithm? Well, B0 will be accessed once in this loop, and this J loop will be run m times. So I'm going to use B0 m times, and we agreed that m is large, maybe in the thousands. So I'm going to use vector B many times, many thousand times. And if this vector B does not fit in the cache, I may have to read it from memory every time that I read it. What about matrix A? Well, in matrix A, it is simpler. In matrix A, I will use every element exactly once. So I will have to read A from top to bottom anyway, so I don't have to worry about data reuse in A. There is no data reuse. But vector B is important. I want to maximize data reuse in B. What is the arithmetic intensity of this algorithm? Well, if n is so large that B does not fit in the cache, then I read two numbers from memory, and I do two arithmetic operations on them. So the arithmetic intensity is 1. I could improve this. Actually, I could make the arithmetic intensity 2 if I reuse B from the cache every time. Then I read one number and I do two arithmetic operations on it. And this one number that I read will be just matrix A. So matrix A is the limiting factor of the performance of this algorithm, but we want to minimize the overhead that reading of vector B gives us. To optimize it, we will use a technique called loop tiling. To understand what's happening in this algorithm, look at this left-hand side panel. I have two nested loops. I goes from 0 to m, j goes from 0 to n, and I'm reading vector b of j in the inner loop. So when I read the first element of b, it's not in memory, so I have a cache miss. I have a pink circle. I have a memory access. In the next iteration, the next value of b will still be read from memory, but the previous value is cached. Then I'm reading this value and the previous two values are cached, and so on. At some point, I will reach the capacity of my cache. Suppose that my cache only fits 4 elements. So when I read the fifth element of b, I will have to kick out the least recently used element, which will be b0. And then as I continue reading vector b, I will only store the last 4 most recently used elements. And the beginning will be gone. The beginning of vector b will be gone from cache. So by the time I reach the end of vector b, the beginning of this vector is gone from cache. Then I increment I, and I revisit b0. Well, I used to have b0 in the cache, but it is long gone. So I have a memory access again, pink circle. As you can see, as memory access to vector b goes, I'm always reading it from memory. Now let's assume that I can rewrite my code in this way. I have 3 loops. One goes in JJ from 0 to n with a stride of 4. The other is unmodified. This is the loop in I. And the fourth one goes in J from JJ to JJ plus 4. So the innermost loop has a length of exactly 4. So when I read the first 4 elements of vector B, they're all memory accesses. They're all cache misses. But when I increment, then I'm done with this loop. I increment I, and I jump to I equals 0. All of these elements are now cached because I have not exceeded my cache capacity. And the second iteration will be fast because I'm going to read from cache. The next iteration will be fast, the next iteration will be fast. Finally, I reach the end of the loop in I, and I go to the next value in JJ. In other words, I read the next tile in B, and I keep reusing it. You can count the number of yellow and pink circles and find that the cache hit rate here is 75%. This is, of course, specific to the tile size and to the cache size that we chose here. This will improve performance by increasing the temporal locality of data access. If I read some value, I will reuse it as soon as I can. This technique is called loop tiling, and there are many approaches to it. What I used here is called cache blocking. And the way to get from original to tiled involves 2 steps: strip mining, which we've already seen before, and loop permutation. These 3 panels illustrate how to get it done. So this is cache blocking. I begin with a code that has 2 nested loops, and if I find that I want to improve the memory access, the temporal locality of memory access in the inner loop, then I will first strip mine the inner loop. You can recognize this. I'm sorry, this is a bug. This should have been JJ, but the approach is clear. I strip mine the inner loop, and then I permute the outer 2 loops. See, I swapped lines 2 and 3, and this is what gets me to the tiled code. So this step 1 actually gives me the same exact code as I started with. Step 2 gives me memory optimized code because the inner loop is short and I'm going to revisit these values, the recently used values of j, very soon. The value of the tile usually has to be chosen empirically, meaning you have to pick some value and experiment in the neighborhood of your guess. Typically, you will find that tiles that are multiple of 16 in single precision or 8 in double precision work best because you have an even number of cache lines here in the inner loop. Also, this technique only works exactly like that if n is a multiple of tile. If it is not a multiple of tile, you may want to either require that it is a multiple of tile, and the user can do it by padding the inner dimension, maybe with unused variables, or you will have to write a remainder loop. I wouldn't try to do anything smart here, like doing a variable termination condition in this loop. I would keep it simple and then write redundant code with nested loops because, well, it's been shown many times that redundant code allows the compiler to better compile. I'm sorry, that having the same, that having the loop length known at compile time allows the compiler to better choose the optimization strategy, even if it costs you to have redundant code. Now, loop tiling can be done as I just described, strip mine the inner loop, permute outer loops. But you could take a different approach. Strip mine the outer loop. See, I strip mine the loop in I, and then permute the inner two loops. This is also loop tiling, and this improves data reuse in processor registers. So it's called register blocking, or another word for it is unroll and jam. This usually works with a small size of the tile, and there is a very important aspect. So when I permute the inner two loops, the inner loop is now in I. As you remember, the compiler always targets for vectorization the innermost loop. So there will be a very significant change going from here to there, in that compiler will now try to vectorize in I rather than in J. This is where you can pull out of your pocket this compiler hint, pragma SIMD, and you can put it before the loop in J. So if you want to retain vectorization in J, you put pragma SIMD before this loop, and then the compiler knows that you want to vectorize loop in line 4 as opposed to the innermost loop in line 5. So what will happen after vectorization is the compiler will take the loop in J, it will split it up into chunks of 8 or 16 iterations, depending on your vector length, and each chunk will become one vector iteration. So it will load a short vector of b's, and this inner loop will actually be unrolled, or maybe if tile is long, it may be actually executed as a loop, but if tile is short, it will be unrolled, and you will use a short vector for b in this computation. And the advantage here is that this first vector in J, you will use as many times as tile. So you will increase your arithmetic intensity by a factor of tile. Once again, this usually works with a small value of tile. You will find that 2 or 4 sometimes work best. This one you have to tile to the size of the register file in your architecture. You have to tune to the size of the register file. This trick with pragma SIMD works just fine with the Intel compiler. If you want to see what exactly happens here, or if you want to implement it so that other compilers can pick it up, you can do unroll and jam using double strip mining. So if you strip mine both loops and then you permute the inner two loops, this is what will happen. The inner loop will be in J, and the length of this loop will have a length that we will have to pick as the length of your vector register. And then outside of this loop you have the loop in I, which increases your data reuse, and then outside of that you have the loop in J. So this code is equivalent to the code that I showed in the previous panel with the Pragma SIMD. So this is exactly the same as that. So this is what Unroll and Jam does. Let's go back to our example of matrix vector multiplication and implement tiling there. To implement tiling, we will strip mine the innermost loop and permute the outer two loops. And the size of the strip we will have to pick and experimentally tune. I tuned it and found that values of a few thousand work best, and I also want to keep these values a multiple of 16. So now, after loop tiling, something important changed. In the original code, the parallel loop was the loop in I. But after loop tiling, I had to move the loop in JJ to the top position. So now I'm actually parallelizing in JJ. This has a very important consequence for memory access here, in that different threads can operate on the same value of I. And if different threads operate on the same value of I will have a race condition here. To avoid this, and to at the same time have efficient code, I will use the pattern of parallel reduction that we saw already several times throughout this course. Last time we saw it in session 7, where we talked about histogram calculation. And this pattern involves splitting the pragma OpenMP parallel 4 into two pragmas, one OMP parallel, another OMP4. I do this so that I can declare thread private variables. So this temp C will be vector C private to each thread. And then I will use temp C in my calculation. And at the end of the main loop, I will have another loop that performs reduction. All thread private copies of vector C are reduced, in other words, aggregated into the shared container. And I use a lightweight mutex, Pragma OMP atomic, to do that. So as long as this loop has a lot more work than this innermost loop, this mutex will not slow down my calculation too much. So back again, I had to do loop tiling to improve the memory access locality. When I did loop tiling, my outermost loop became the loop in J. So now I have a race condition in in the calculation of vector C. To deal with the race condition, I used thread private variables and parallel reduction as we discussed earlier. Now, we dealt with it pretty well, but there is another problem that occurred after loop tiling. I used to have the outer loop in I, which, as we agreed, has thousands of iterations for our target problem size. But now the outermost loop is in JJ. How many iterations does it have? Well, it has n divided by jtile. So we have either to do some careful balancing here, meaning jtile cannot be too small, because if it's too small, then I'm not using the entire capacity of my cache. But if it is too large, then I may have too few iterations here. So if n is only in the thousands and jtile is 4,000, I may end up with a situation where I have just a few iterations in the outer loop. And this should immediately remind you of a problem that we dealt with again in session 7, where we had a matrix where we swept along the rows of the matrix, and this matrix only had 4 rows and many columns. It may have looked like an artificial problem back then, But now I'm presenting to you an example where exactly this situation may occur because you did some other optimization which caused your outer loop to be very short. If you have too few iterations here, you will not have enough workload to utilize all the threads that you have. But thankfully, because of the previous discussion in session 7, we know what to do with it. We can expand the iteration space by using loop collapse. But prior to doing loop collapse, you can convince yourself experimentally that it's good to strip mine this loop and maybe permute the loops in II and JJ. So this slide shows the fully optimized version. So compared to the previous slide, now I strip mine the loop in I, and I'm collapsing loops in II and JJ. The loop collapse is to expand the number of iterations available to OpenMP. So now instead of n divided by j tile, how many iterations do I have? I have n divided by j tile multiplied by m divided by I tile. So if m is in the thousands and I tile is, well, 64, I may have tens of iterations here, so I may end up with tens or maybe hundreds of iterations in these two collapsed loops, enough to utilize all my cores. Loop collapse, once again, tells OpenMP that you want to parallelize across the Cartesian product of this iteration space and that iteration space. And then for each thread, you have this loop which performs matrix vector multiplication. I have to say that this code listing is my favorite code listing in the entire course because it blends so many areas of optimization that we have addressed earlier. We have thread parallelism, and we have techniques for expanding the amount of parallelism. We also have an illustration of using thread private variables to minimize the amount of synchronization and avoid race conditions in the parallel loop. It illustrates using mutexes to protect race conditions where it is safe to do that. And it demonstrates vectorization in the innermost loop, assisted by compiler hints that allow you to drop peel loops and save time on initialization. It also illustrates how to align some of the values on stack, and we are assuming that matrix A is aligned on the heap. So all of these topics we have discussed earlier, and they come together in this code to improve performance. Now it would be a good time to show you the performance results, but before I go to performance results, let me first ask you this. Take my word that these optimizations improve performance to a good degree. But before we go to the results, I will show you another way to optimize memory access pattern in this algorithm. So we discussed loop tiling. And to tile your loops, you will have to do a lot of experiments. You will have to decide, are you going to do unroll and jam, or are you going to do loop cache blocking? In other words, are you going to tile the outer loop or the inner loop? You will have to pick the optimal value of the tile size, and then you will probably find that the optimal value of tiles are different for Xeon and Xeon Phi. By extension, you can assume that if you move this code to a different platform, you will have to tune the values of tiles once again. This is not desirable, and some people might want code that is more portable. Also, you will find that the optimal order of loops may be different for different platforms, and this is a whole can of worms now, right? Because I may have to tune for every different platform, and it is more difficult than tuning a numerical parameter. So something that's more stable across different platforms would be welcome, and this can be achieved with cache oblivious recursion, which is a self-similar algorithm. So this is matrix A, and I have a diagram that illustrates how we are traversing matrix A. I have these big big rectangles. These big rectangles illustrate the tiles in my loop. Oh, by the way, it's called tiling because, well, if you look at the innermost loops, this is a tile, 64 by 4000. So these are tiles, 64 by 4000. And then I have tiny circles inside of each tile representing elements just for visual illustration. So the way that I traverse tiles in my blocked algorithm is from left to right, then the next row of tiles, and the next row of tiles, and so on. The numbers map out the order in which I traverse tiles. And when I read vector B, I read this part of vector B corresponding to tile 0 many times, then I read the next vector B corresponding to this tile many times, and so on. So there is a trade-off. Either I will read matrix A sequentially, but then I reuse this part of vector B a few times, and then I come back and I have to read it from memory and reuse and so on. Or I could change the order of tile traversal and go from top to bottom, from top to bottom, from top to bottom. This would improve the data access to B, but degrade the data access to A, because I will have going from top to bottom, going from this tile to that tile, I jump in memory locations because my matrix is row major. Instead of doing that, I could change the order of tile traversal, and I can do it using, I can find a trade-off between the optimal access to A and B by doing a recursive approach. Let's look at this matrix first and think, is it too wide or too tall? And let me decide that it is too wide for its height. Then I will split this matrix horizontally, and I will recursively do matrix vector multiplication using the left-hand side and the right-hand side of this matrix. So I do this kind of split. Then when I recurse into the left-hand side, I look at the matrix shape. Oh, now it's too tall, so let me split it vertically. Now it's too wide, split horizontally. Too tall, split vertically. Too high, horizontally, and so on. And I will recurse down until my submatrix is small enough. This small enough is going to be determined by some recursion threshold that I'm going to set in my algorithm. And once I reach the recursion threshold, I'm assuming that the subset of vector B that I'm dealing with fits in the cache. And as you can see, when I recurse out, the order in which I visit tiles is going to be self-similar, like that. So wherever I start in my algorithm, I will stay in the vicinity of the starting point for some time. And you can use that I'm more local in my memory access to B. See, I'm revisiting B sooner. The idea of this algorithm is that there is only one tuning parameter, the recursion threshold, and I can afford to misjudge this recursion threshold. Specifically, I can err on the small side. If I set my recursion threshold too small, it is not a problem, because I will keep splitting up my problem within a domain which already fits in the cache. So if my cache is big enough to fit, say, this big of a tile, but I keep splitting it up some more, it doesn't matter, because when I start recursing out, I still stay within that tile. I still stay within the cache. This kind of approach, recursive divide and conquer, recursive cache oblivious algorithms, can be applied to a number of algorithms. A very famous one is the Cooley-Tukey algorithm for discrete fast Fourier transforms. Recursive approach helps you to make it self-similar. And for example, the FFTW library is built largely on cache oblivious algorithms. And actually, one of the authors of that library is one of the authors of the cache oblivious algorithm family. What will it look like in code? In code, to implement cache oblivious recursion, I will use OpenMP tasks. The code may look scary, but it is actually easier to write than it is to read. In this code, I will have a recursive function. It will take matrix A and B, which will actually be submatrix of A and submatrix of B. Then I will decide on recursion thresholds. And if I see that matrix is smaller, that the submatrix is smaller than this recursion threshold, I will just run matrix vector multiplication without any tiling, just two nested loops. This is what I'm not showing in line 6. But if the matrix is bigger than the threshold, then I will see, is it too wide? If it is too wide, then I will split it vertically. So I will make two recursive calls. In one recursive call, I split the value of m, and the other recursive call, I split the value of m and start with an offset. And then I put the first recursive call into an OpenMP task. So it runs in parallel with this call. I will have to wait for this task using OpenMP task wait, and then I accumulate the results. And then there's another version of this branch which will do a similar thing for splitting the matrix in another direction. So what's happening here is basically constructing a recursive tree of tasks and allowing OpenMP to schedule these tasks so that they don't oversubscribe the system. Finally, let me get to the performance results. And compared to examples that we showed, that we discussed earlier, the difference between before and after is not as striking. Well, it is pretty good. I got something like 40% improvement. But still, this is not as striking as 1000x improvement that we saw earlier. I have to explain that in this matrix vector multiplication code, the majority of time is spent reading matrix A. And we cannot do much about that. This is a bandwidth-bound application. What we were doing all along is reducing the overhead of reading vector B from memory. And reading vector B from memory can as much as double the memory access pattern. So the maximum improvement that we could expect is a factor of 2, but actually slightly less than that for the problem that we chose. We are dealing with a simple enough problem. I just want to make a disclaimer that in other applications you will find that loop tiling has way more dramatic consequences than what I'm showing here. I'm showing matrix vector multiplication because it's easy enough to understand in the training setting. So we started here. This is the unoptimized code on Xeon and on Xeon Phi. Then we tiled the J loop, and it improved performance on both platforms. But this time we found that there is not enough parallelism in the outer loop. And to fix that, we strip mined the loop in I, collapsed loops, and also I found that permuting some loops is also useful in this case. So in fact, I tiled the I loop, and it improved performance some more both on Xeon and on Xeon Phi. Now I found an implementation which is tiled and gives me a higher performance on Xeon Phi. But in fact, the same implementation drops performance on Xeon Phi. And also, this is not yet the peak performance that we would expect. So after trying tiling, I tried the cache oblivious recursive algorithm, and it improved performance both on Xeon and on Xeon Phi a little bit more, and it is a bit more stable with respect to changing the tile size. And I expect that this algorithm will port, for example, to the next generation of Xeon Phi better than the tiled algorithm. We will experiment with this in the hands-on part. So hopefully this is going to be, you will find it useful in your work. But before we finish with the presentation, I want to demonstrate a few additional considerations for memory traffic optimization. One of such considerations is first touch allocation. So let's forget about loop tiling and memory access pattern. Let's focus on something that's really tied to the architecture. So I'm using for all my tests a dual socket Xeon. So I have a system board. It has one CPU package, another CPU package, and there's memory modules. These memory modules are local to this CPU package. Those memory modules are local to that CPU package. And if this CPU package wants to talk to memory in those remote sockets, it can. To the programmer, it is absolutely transparent. But architecturally, it has to go through a switch on this board, which we do not see, called QPI, Quick Path Interconnect. So it accesses a remote memory through the switch, which has lower bandwidth and higher latency. So we have a system that has twice as many cores as one CPU socket would give you. It has support for twice as much memory as one CPU socket could support, but the cost is that now we have a NUMA system, non-uniform memory access. So depending on where your memory sits, you may have either local fast access to it or remote slow access to it. This applies to multi-socket Xeons. It will also apply to the second generation of Xeon Phi. Intel has not announced exactly what will happen with NUMA in the second generation of Xeon Phi, but they have announced that the second generation of Xeon Phi will have NUMA support. So in other words, stay tuned. But in the context of NUMA systems, it is important to understand how Linux allocates memory. And the policy is first touch by default, which means that when you call malloc, you're telling the operating system, I will want 1 GB of memory sometime in the past. But where exactly this memory is going to be placed in physical memory modules depends on who touches it first. Let me go back to the previous slide for a second. If I have an array, I allocate it, and then I initialize this array with one thread running on this CPU, then this CPU will be the first to touch that array. So the virtual memory pages that hold this array will all be placed on memory modules local to the CPU. If I do that, I initialize with one thread, the entire array will end up on the CPU socket. And when that CPU is going to try to use that memory, it will always have to go through the QPI and it will slow things down. A better way to do that is to allocate my array from a parallel region, like that. So I have a matrix which I want to initialize with zeros. Instead of using memset or just two nested loops running serially, I better put in pragma OMP parallel 4. It will speed up the initialization, of course, but it will also speed up subsequent calculation because my memory is going to be distributed between the two CPU sockets. And if I touch with the same pattern with which I'm going to use, I will have a favorable first touch allocation so that each thread is only going to talk to its local memory. This is just to illustrate the importance of initializing data from a parallel region. It's important not just to speed up the initialization, but also to speed up subsequent processing if you have a NUMA system such as a dual socket CPU. And another technique that I wanted to really quickly illustrate, time permitting, I will show a lab for this, is loop fusion. This is a technique to improve memory access locality in applications that have a pipeline structure. Suppose I have many data elements and I want to put them all through pipeline stage of some data processing, number 1, and then pipeline stage number 2 of some data processing. I could implement it like this. I run through the entire data set using pipeline stage 1 and then through the entire data set using pipeline stage 2. Or I could do it like this. I put one element through pipeline stage 1 and then the same element through pipeline stage 2. You can immediately see that this is more efficient. The fused loops are more efficient because the memory access pattern has better locality in time. Instead of going through the entire data set and then revisiting it, I'm reusing each data element many times. The danger of this is that if you have so much data that it overflows the cache, then by the time you reach the second loop, you will lose all your read elements from the cache and you will have to read them from memory again. This is better because this has better data locality, and also it may help you to reduce the scratch data footprint. This is the performance results from one of the labs that discusses this specific example. So today we talked about memory traffic optimization, and I really tiled on loop tiling, which is a relatively easy to understand technique that improves memory access locality and time. There are two flavors of loop tiling: cache blocking, when you strip mine the inner loop and permute outer loops, and also unroll and jam. This is where you strip mine the outer loop and then you permute the inner loops. Potentially you have to direct the compiler to vectorize the middle loop. There is also cache oblivious recursion. It may not be as easy to understand. It may be a little bit more tricky to implement, but it is more portable than loop tiling and achieves essentially the same effect. I also talked about first touch allocation in NUMA system, and the bottom line advice is initialize data from parallel regions. Ideally initialize data with the same pattern with which you are going to access it. And I briefly talked about loop fusion, which is a technique that helps you to improve data access locality a little more. This was a very intense uh, session. I hope that you were able to understand the principle, and we will strengthen that by repetition in the hands-on part in the second hour. In the next session, I will talk about performance analysis, vTune, and performance out of the box with the Intel Math Kernel library. So because we are running slightly past schedule, I'm going to declare a 2-minute break. And if you have any questions, please type them in the questions box during the break. So see you in 2 minutes. All right, I am all set up to begin the hands-on presentation. And we are going to work with lab 408. Now, I want to make a disclaimer here that when you are connecting to training servers, you are accessing a virtual machine. So your CPU is virtualized. I think that some of the performance optimization steps are not going to be reflected accurately in your virtual machine. But everything that we do will be reflected perfectly accurately on your Xeon Phi coprocessor. So if you go by the Xeon Phi performance, you are really measuring what you should be measuring. Your Xeon Phi is not virtualized. When you're working with Xeon Phi, you're actually running in hardware. So our lab 408 is exactly what we discussed in the hands-on in the lecture part. This is matrix vector multiplication. I'm timing the function multiply, which is written out here. Pragma OMP parallel 4. It parallelizes the outer loop. Pragma vector aligned is a hint for vectorizing the inner loop. I can make and establish the baseline performance. So something is wrong with my Xeon Phi. Maybe it was just asleep. Yeah, now it works. Okay, so let me record performance as I got it. On Xeon I got 13 gigaflops per second. On Xeon Phi I got 22. Now, let's see how much performance do we expect. We can estimate this based on this. The most time should be spent reading matrix A from memory. Vector B should really not be a concern. It is m times smaller than matrix A. M is 1000. So if my algorithm is optimized so that I always or almost always reuse B from cache, it should carry a really negligible amount of traffic. But matrix A, I'm reading sequentially from memory with multiple threads. So essentially, I'm dealing with the streaming bandwidth of my memory. And for every number that I read from matrix A, I will do two arithmetic operations, this multiplication and this addition. So let's factor in the fact that the stream benchmark gives me around 60 gigabytes per second on host and 130 gigabytes per second on Xeon Phi. So each gigabyte that I read is 1/4. I'm sorry, each gigabyte that I read is 128 million values of A, and for each of them I do two operations. So I need to divide this number by 4, and this will give me the expected gigaflops per second on each respective platform. So on Xeon, I would expect to get something like 15 gigaflops per second. On Xeon Phi, I would expect to get something like 130 divided by 4, which is 40 or so gigaflops per second. So we are close to the expected value on Xeon, but far from it on Xeon Phi. Oh, not 40, 30. Yeah, this is more like it. So this is what we are going to try to improve. Before we go there, let me show you how to ruin the performance of this application on Xeon Phi by ignoring first touch memory allocation policy. So as I mentioned, my Xeon has two sockets. It has memory modules local to one socket, memory modules local to the other socket, and where the parts of matrix A go depends on who first touches them. Currently, my initialization is done like this. This is my initialization. As you can see, I'm touching matrix A from a parallel region. And I'm doing it, with multiple threads. So now let me remove this parallelism here and take a look at where I'm doing this. I'm doing this in the initialization part. I'm not timing initialization. I'm going to time down the line the multiplication. But let me just demonstrate how to what happens if I don't initialize from a parallel region. The performance drops by a factor of 2 on the host, and it should not change on Xeon Phi. So on the host I got 7.2, and on Xeon Phi I got 22 gigaflops per second. You will probably not see it in your virtual machine because you don't have really a NUMA configuration for it, but I was able to demonstrate it on my physical machine. So let me bring this back. I want to initialize from a parallel region. This helps me down the line when I use it. And make sure that everything is back. As you can see, on the host, I'm also using affinity of type scatter. On Xeon Phi, am I setting affinity on Xeon Phi? Looks like I don't, but by default it is set to scatter. Let me also try to experiment with the number of threads. On the host, I will set it to 12. It doesn't seem to change the results. Just doing due diligence before I jump into memory optimization. And let me try to experiment with it on Xeon Phi. So here in the make file, I will also set KMP place threads equals 1T, meaning one thread per core. We discussed it on Friday in session number 7. And make sure that this doesn't change anything. So why do I have an error? KMP place threads equals 1T. Something went wrong. I think that what happened is I killed my Xeon Phi by pressing Control C when an application was running there. No? Okay, this is a situation that I am happy to illustrate. If something goes wrong with Xeon Phi, it stops running. Sometimes the solution is to reboot it. And the command is mic control -R. And I have to run it as root, so I use sudo. And let's wait for Xeon Phi coprocessors to reboot and go back online. I apologize for this delay, but I think it's good that it happened because I'm able to illustrate what happens, what to do when things don't go right. When Xeon Phi reboots, what happens is it goes to a state where there is nothing in its memory, and it's trying to do essentially PXE boot from the host. The host will actually feed to it the image file of the operating system. So when it's ready, it's waiting for the host to feed to it an image file. And this is the image file that the host pushed across the PCI Express bus to the bootloader on Xeon Phi. Now it's booting with this image. It's creating a RAM disk, populating it with the operating system on in the Xeon Phi file space. And at some point it will change its state to online, meaning that it's fully booted and it's ready to roll. So now I run my application, it runs, and if I try to experiment with different numbers of threads, I want to make sure that I'm using, okay, 1 thread per core is not good, 2 threads per core, 3 threads per core. It looks like 4 threads per core, the default, works the best. Well, maybe 3 threads per core. Okay, let's stay with this and go back to the code and see what we can do there. So the problem with this code is that B is long. B is 2 to the power 19, so in double precision it has 64 megabytes of data. And let me record this. And every thread will have to go in B from 0 to end. So by the time I reach the end of vector B, I've lost the beginning. So let me try to change the situation, and I will do it by loop tiling. So here I will introduce 2 nested loops. One iterates with a stride equal to jtile. Another iterates within that strip, kind of mining it. And jtile I will have to tune by hand. And let's start with something that is a multiple of 16. I know that for cache blocking, usually values of order tens to hundreds to thousands work best, but we will start here just to see the effect of tuning. So what I did now, this belongs here. What I did now is I have the same exact code, just expressed differently. So the performance should not change. But this is only the first step of memory optimization. Actually, performance degraded a little bit because of probably the overhead of setting up this loop. But now I can do loop permutation, and this is probably going to help me. When I do that, the program will not work well, and it's also going to produce incorrect results. Why is that? I used to have different i's distributed across different threads in the parallel loop, but now the parallel loop is in JJ, so different threads may very well work on the same value of I, which means that here I will have a race condition. To deal with this race condition, I will use thread private containers, just like I did in the past, and we already know this parallel pattern. So I'm splitting Pragma OMP parallel into 2 Pragmas, and you will do this whether you're doing Fortran or C++. This allows me to create a thread private variable, and also to create a post-processing loop for reduction. So, so I will do what you will have to do in Fortran so that Fortran programmers can stay tuned. I will create a thread private container, C thread, and it will be as long as vector C. But I will declare it as private to each thread. So each thread will get its own private copy of CTHR. Here I will initialize it. And then instead of using, this is a familiar pattern, instead of using C here, which is a shared variable, I will use CTHR. And then at the end, when the main loop finishes, this is the main loop, I will reduce, in other words, aggregate across all threads into the shared container. We have seen this pattern many times, so I'm not going to spend too much time on it, as long as I don't have bugs. And this is going to reduce from all threads into the shared container, but there is a race condition here. So I will put pragma omp atomic. This is an atomic mutex that guarantees that I will have correct results here when different threads are writing into the same container. So let's see if this works. Illegal operation. Oh, I need to accumulate. Now I have a segmentation fault, meaning that I messed up somewhere, and this is where I messed up. Okay, so now there is no complaint about correctness. The program produces correct results, but it is slow. Because it is slow, my conclusion is that I probably don't have a good value for the tile size. I know that for loop blocking, I usually need to have larger values. So I will start increasing it until I hit something that looks good. There is a trade-off. If it's too small, then I'm not using my entire cache. If it's too large, then I am spilling over the cache, which is not good either. So as you can see, this was good for the Xeon Phi. It was not particularly good for Xeon, but at least we are in the right neighborhood. And because I didn't want to make the code too complex, I am limited to, well, values of JTile which divide n. So n must be a multiple of JTile. I could potentially do slightly finer tuning if I wanted to go in and implement a peel loop somewhere here, but I don't want to spend time doing that. Just crude tuning is good enough. Okay, so this seems like the best result. On the host, I'm getting 12.2 or 12 gigaflops per second. On Xeon Phi, I'm getting 26 gigaflops per second. So that's an improvement. But now I have to focus on what I'm getting here. N is 10 to 19, 2 to the power 19. So n divided by JTile is, well, this is 2 to the power 12, is 2 to the power 7, which is 128. This is not enough for 240 threads. To fix this, I will try to strip mine the inner loop in I, and we already saw this in episode 7. This is just to expand the amount of parallelism that I have, that OpenMP sees. So the outer loop will iterate with a stride of I tile. The inner loop will iterate with unit stride, and I have to introduce the value of I tile. And the value of I tile can be anything. Let's start with 2. And this allows me to use the collapse statement. I have to spell it correctly. So this seems to work for Xeon Phi. I'm getting slightly better. So if I play around with it, we will see. So about the same, but I know from experience that at this point it is time to think, well, maybe I need to play with the loop scheduling mode or with the order in which I visit my tiles. So I will try, for the purpose of experiment, to permute these loops. As you can see, this is better for the host, about the same for Z1Fi. Maybe a little, no, actually a little worse. So how about changing the loop scheduling mode? Well, basically, I've gotten somewhere where I want to be. I'm getting around 13 gigaflops per second on the host, which is actually not, well, not even that much. Yeah, that seems to be better. But now on Z1Fi, this is not too good. How about permuting the order in which I visit cells again? No, this didn't work. So let's see if this helps. A lot of tuning to get really marginal improvements. Well, this seems like the best. Oh. And maybe I will have to conclude that I have to have different values of tuning parameters for the host and for Z1Fi. So let me try that. So on Z1Fi, I will have this value. And on the host, I will have a different value. I should have recorded this because now I don't remember anything. Where did I get 27? I seem to have lost this well, just as an illustration. Okay, so 14. Well, I saw 27 somewhere, but this is a marginal improvement for a lot of tuning work. Well, at least at this point, I've demonstrated how to use loop tiling. I want you to take my word for it that the effect of loop tiling on performance is much more dramatic than in other applications than in this one, because here we're actually improving this part, but the dominant contributor to the execution time is that part, and we cannot do anything about it. So at this point, I propose to give up on further improvement and just announce that, well, we have done what we could to get the actual performance as close as possible to the theoretically expected performance. And we saw that loop tiling helps, but I need to experiment with the tile sizes and possibly experiment with at least one tuning parameter, or maybe I would have to experiment with two tuning parameters. And this will be, well, exponentially, with every parameter you exponentially expand the number of trial runs that you have to do, and you have to do it for every platform. So this is loop tiling, and I want to demonstrate an alternative approach to parallelizing this application, which may be a little bit more stable across different platforms. So I will do it like that. I will how many? Okay, so I will just keep this for reference. I will comment it out. And let me go back to the very original implementation. I had pragma OMP parallel 4. Then inside of it I have the loop in I going from 0 to n. And then inside of it I have a loop in j going from 0 to n. So this is our original implementation. Right, let's double check that it produces correct results. It doesn't, so where did I make mistakes? I goes to m and j goes to n. Okay. Okay, I'm back to square one. So let's see if I can do it in a more portable way by using recursion. To use recursion, I will do this. Well, I will do it nicely this time because I think we have enough time. I will call it multiply. I will have one function which I will call multiply. It will have the same exact interface as before. And then I will have a helper function called multiply engine, and it will take one additional parameter, LDA. This is the leading dimension of A. We will see in a second why we need this. And from this function multiply, initially I'll just call multiply engine A, B, C, N, M, and the leading dimension of A is actually equal to N. Let's double check that this works. It works. And now you will see why I did this. I want to use OpenMP tasks. And to use tasks, I will do this pragma OMP parallel. It will create multiple threads. I will immediately restrict execution to just one thread. And then I will use tasks from within that function. This is the pattern that we have to use with tasks. I've discussed it in session number 4. If you want to revisit it, the session number is 4. So at this point, let's get rid of parallelism here. We will have single-threaded implementation, which will be slow, but at least correct. And now let's focus on the recursive algorithm, which will have this pattern. We will look at the matrix and see, is this matrix too wide or too tall? What is too wide and too tall is up to us to decide, but if we decide that it is too wide, we will split it like this. If it's too tall, we will split it like that. And we will keep splitting until we've reached the recursion threshold. So let me define some recursion threshold. And I will initially set it to 16 by 16. And I will check. If m is less than or equal to I threshold, and n less than or equal to j threshold, then I will actually run this exact loop. So I'm assuming that I'm already dealing with a subset of matrix A. But if I have not reached the threshold, then I will have a check. Is the matrix, so this is now we will check if the matrix is too wide or too long. This is how I will do it. If, well, it is too wide means that the value of n divided by j threshold is more than m divided by I threshold. And I will label this case, this branch as matrix is too wide. Otherwise, matrix is too short. And the threshold check should be in multiply engine. You will see in a second why. You will see it once I write out the calls, the recursive calls. So we don't see recursion yet. A recursion will occur inside of this multiply engine. This function multiply is just to preserve the interface. So if the matrix is too wide, and let me rewrite this, I'm not comfortable with integer divisions, so I will multiply both sides by I threshold and by j threshold. So I want to rewrite this like that because I don't like dividing, especially by integers. I think this is the same expression, just safer. Okay, so if it's too wide, then in my recursive calls, I will have to reduce n. Okay, so I'm making two recursive calls. Now let me think of how to make them correctly. So in the first recursive call, I want to, in both recursive calls, because n is too large, I want to reduce the value of n. And n is also the size of C, so that's what I will have to do. I will have to create a copy of C. I will call it C1 or C, yes, C1. No, C has the length M. Yeah, I will create a C1, yeah, and it will have length N. Do I need to initialize it? Probably yes. And I will then run this. And the matrix that I'm sending is going to be like that. Actually, instead of n, I have to use LDA. That's the point of this. LDA is just the physical size of the rows. And I want the address of the first element. And instead of vector b, I will pass the address of the first element of vector b. And then I will pass vector c1. And then here I will call, so I am splitting n, which is j. So I want to start yes. So here I'm passing in the left-hand side of the matrix. Here I'm passing in the right-hand side of the matrix. And here I'm passing in the top of vector b, and there I need to pass in the bottom of vector b, and this will compute into vector c2. So I think this is the correct first recursive call, but I will have to do this aggregation. And the second recursive call will be the opposite. I will make two recursive calls to multiply engine, but I will split the matrix in a different direction. So the first call will be this. And I will pass in the, well, still C1. And the second call will pass the bottom of matrix A, which is like that. And then, yes, I think this will work. So C1, I need this, but its length is actually sorry, C, how long is C? C is actually M elements long. This is a bug. It should be M. Then C1 is going to be M divided by 2. C2 is going to be M divided by 2. And here I'm passing C1 and C2. And then I need to aggregate like this, C0 through bugs, be gone. And thank you for catching my bugs as I type. Well, now let's see if it compiles. It compiles on the first try, which is suspicious. So let's see if it produces correct results. I don't have any parallelism yet. This is just recursive call. And yeah, it breaks, well, because I've recursed too much. Well, actually, I don't have to have this check. Okay, segmentation fault means that I have to double check my solution. So here, this is right. So if n is too large, I'm going to split n. N is the length of vector b. So I have C1, C2. And C1 left-hand side of the matrix, C2 seems correct. And here C1 is M over 2. Yeah, this seems like a bug. So now it's computing slowly, but no complaints about correctness. So I've implemented the correct implementation. And before I try to parallelize it, let me try to tune my parameters so that I have a decent performance in at least the initial implementation. I think I have to increase the thresholds. This seems to be going in the right direction. And just from my knowledge, to avoid wasting time, from my knowledge of the tiled algorithm, I will pick these I threshold, J threshold, similar to what we found in the tiled algorithm. And then I will demonstrate to you that I have better flexibility than in the tiled algorithm with these parameters. Well, in other words, I have more room for error. So this is the performance on the host. We will see performance on XeonPhi in a second. XeonPhi is doing something with one thread, not very efficiently, but still. So how do we parallelize this? Well, I was going to use tasks, and to use tasks, I create threads that will handle these tasks. And then I will make the initial call to my function from a single thread. So now I have many threads spinning, waiting for tasks. And all this function has to do is to spawn off these tasks. So I will wrap the first call to this function into pragma omp task. And I think this is all I have to do. Similarly, the second call will be wrapped into tasks. And I have to be careful here. See, I have a line where I use C1. C1 is supposed to come out of this task. But what will happen is, because this is a task, OpenMP will schedule this function for execution sometime in the future. Or you can think of it as this function will run in parallel with the rest of this function. Then immediately control will return here, here, and so on, and I may end up computing this line before this task completes. So to wait for the task, I will have to use pragma omp task wait. And this will create a recursive tree of tasks, because when I go into this function, I will go through this again, check for the threshold, no threshold, again, okay, then spawn some more recursive tasks. So I have to put this here, 2 OMP task wait regions, and let's see if I get correct results. So I get correct results, and performance is decent. Yes, this is the performance that we saw with the optimized version. But before I leave, I want to look at the tuning parameters. So this is related to a question that just came in. How many levels of recursion do we have, and how many would be too much? Well, we can estimate this. So our matrix is m times n, where m is 2 to the power 10, and n is 2 to the power 19. Then my threshold is 2 to the power, well, I threshold is 2 to the power 5, J threshold 2 to the power 12. So to get there, I will have to split 5 times in I, 7 times in J. So levels of recursion are 10 minus 5 plus 19 minus 12, which is 5 plus 7, 12 levels of recursion. And how many serial instances, how many functions reach this threshold? Well, this is 2 times 10 divided by 2 times 5 multiplied by 2 times 19. This is how many tiles I have, divided by 2 times 12. This is 2 times 5 multiplied by 2 times 7. This is 496, coincidentally. So we need, with this recursion threshold, we need to have a balance. We don't want recursion threshold to be too small, so that there are very few, a huge number. So there is a huge number of functions running, but we don't want it to be too large, so that we have memory issues in the serial implementation. Now, how many levels of recursion is too long? I don't have a ready answer for that, but this is, I believe, limited by the stack size. So, however, yeah, you need to fit all those recursive functions on the stack. I think. Give me a second to think. 14, 7. Yeah, I think 12 levels of recursion is not too much, but we can see if we can break this. Does this break it? Yep, that doesn't seem to break it. How about this? So I can have many levels of recursion and it doesn't, well, and it doesn't. Yeah, so with as many levels of recursion as I could afford, it still worked. So in this case, the number of levels of recursion was 7 plus 14, so 21. 21 levels of recursion was not too much. But as I mentioned, this is an issue with tuning, and I have more room for error. So if I guess on the small side, on the low side, my performance will not degrade too much. And if I guess on the small side even more, I'm still going to retain data locality. If I guess on the large side, it will probably, well, actually, this is not so bad. Yeah. So I have more room for error. I have basically anywhere from 2048. These produce almost the same results in the recursive algorithm. In the tiled algorithm, this is a very different story. I had really significant performance deviations, and let's confirm that. So once again, I have 26, 27, and 27. And now let's see what we had with the tiled algorithm. So I will comment out this function, and I will bring back to life the tiled function and try 2048. This is the wrong run. On Xeon Phi, we used to have 26 in the tiled algorithm. Now we have 21. Now this gives the optimal performance. And we used to have 26 on Xeon Phi with this setting. With the tiled algorithm, well, it's still not so bad. So, well, at least another factor of 2 in the value of the tiled parameters. This is the flexibility that I have. Now, when I'm doing this, I'm creating thread private variables for every level of recursion. I'm assuming that C1 and C2 fit on the stack. If they did not fit on the stack, there's two options that I have. I can possibly increase the stack size. I could possibly create them on the heap if this doesn't cost too much in performance. But in any case, you have to realize that I will have to have a lot of thread private data for this. I will have to have as many copies of this data, I think, as I have these functions running. But every copy is half. Yeah. So yes, there's no way around using extra memory for this, but I guess this is where tuning kicks in, and you don't want this too small, you don't want this too large either. I mean, the threshold parameter. I would not try to allocate this on the heap inside of the parallel region, because at least on Xeon Phi, malloc serializes execution, and you would lose performance. But allocating this in advance and then somehow figuring out how to use the pre-allocated containers inside of the parallel region, that seems to be a better strategy. We saw two methods of memory optimization for the matrix vector multiplication problem. Loop blocking, cache blocking, which is a loop tiling algorithm, and cache oblivious recursion. Cache oblivious recursion, in my opinion, may be more stable when you port it to different platforms. It may be a little bit more tricky to implement, but we saw that, well, there's less parameters to experiment with. The performance increase that we saw was not as huge as in some of the other exercises that we did, but this is because we chose intentionally a simple enough problem to understand. Well, the cost of that is that most of the time we are reading matrix A. If you want, try to experiment with matrix multiplication and see how far you can get in performance with that problem. It will be a bit more challenging. I had one more lab planned for today, but I don't want to squeeze it into the last couple of minutes of this session. But if you have time, go to 409, and it demonstrates loop fusion as a method for increasing the temporal locality of memory access. With that said, I want to wrap up this presentation. If you have any more questions, type them in the question box even after I disconnect. Otherwise, I will see you tomorrow for the last presentation, where we will talk about two performance tuning tools, two software optimization. Well, we will talk about two software development tools. One is a performance analysis tool, Intel vTune Profiler XE, and the other is performance optimization tool. You can think of it like that, the Intel Math Kernel Library with support for Intel Xeon Phi coprocessors. So thank you very much for your attention. Hope to see you tomorrow. Bye.